I don't have a lot to say on the syllabus because hopefully you have taken a look at it already. The big things are textbook access. So I've said a little bit about that in my opening email, and we use the Pearson textbook for this. I don't really have a say in that, but I actually like this textbook. Of all the classes I teach, it's actually my favorite textbook. So it's Conceptual Physics by Paul Hewitt. You don't have to have a physical copy. You can just get the online access, and that includes all the stuff you do homework on, and I'll show you that in a bit. And it includes a e-textbook. So I know even still a lot of people are varied on how they feel about e-texts. So if you want a physical textbook, you can still find them pretty cheap. And especially for just reading the textbook, you don't have to get this edition. So for access, for the online access, you need 13th edition. But if you just want a physical textbook to read, you can go 12th, 11th. Not a lot changes as far as the text part. And I hate that that's how textbooks work nowadays, but anyway. So for that access, if you are in Smart Start, you should be good to go. I'll show you how to get that code that you should have generated for you. If you are not, you will have to, by the end of a trial period, you can have set up, get access to Pearson, and that should also pop up in just about the same way. So I'll also show where you would go for that. Let's see, grading, the big thing point out is homework. It is by far the biggest chunk. So I would definitely keep on top of that. As far as extensions go, the homework should be set to just reduce the grade by 5% every day up to a maximum of 20. Under extenuating circumstances, extensions without any drop in the grade is also a possibility. It's just you got to let me know, and ideally ahead of time. Extra credit. So you can, by the end of the semester, do a few things to increase your grade by up to 5 points. And that does mean that if you end the semester with, say, 80 points, you can end up with 85. And how you can do that is you can either attend seminars that the department hosts. They're usually every Friday at 3 p.m. in Manning 201. And I'll send out reminder emails when I hear about them. Usually they don't tell us when they're going to happen until a day or two before, but they're more or less weekly once they get rolling. There's also going to be some things you can do in Canvas, and they'll just be called extra credit activities. Those aren't up just yet, but will be very soon. There are quizzes, but they're not a big thing. They're not pop quizzes. Finish a chapter, you will have a 5-minute quiz with 5 questions, all multiple choice, all concepts, no calculations. There's very few calculations in the class. And it's just kind of to check up on how that chapter went. So those are only 10% of the grade. If you completely fail every single one, you can still get technically a 90 in the class if everything else goes fine. So they're not something to stress over. They're just something to kind of take a quick look over the notes before the quiz, and it should be okay most times. Okay, that is the main things from the syllabus that I wanted to touch on. Office hours. So I am in Manning 220, and that is very close to our classroom. If you are standing at the entrance of our classroom and you turn right and go down the hallway, you'll see me on the right eventually. So if you have any questions, my official office hours are 1 to 3, but if you just happen to be walking by and have a question, I'm happy to answer them. I'm also happy to answer questions at any time over email, day or night, weekends, whatever. Just send an email if you have a question, and as soon as I can get to it, I will answer it. Pearson, that's the other thing. So, the first thing is if you are in Smart Start, and if anyone's not sure what Smart Start is or if they're in it or not, you default to being in Smart Start, but you can opt out. And I believe the opt out date is January 26th. It's an alternative way of paying for textbooks where instead of paying by the textbook, you're paying by credit hour. And I think it's still $24 per credit hour. So you'll just want to see what works better for you, what's cheaper for your specific number of classes. Is it cheaper to go by credit hour or the actual number of books you have to purchase? Because even if a class doesn't have any textbooks, it still counts towards those credit hours, unfortunately. So if you have Smart Start, you go to course materials, there will be a link that's generated. You copy that link. So it'll be down here. You copy that link, you go to Access Pearson, and you'll open Pearson. It'll ask you to create an account if you've not had one for anything else. And then it will ask you for that code, and you just paste it in. If you are not in Smart Start, then all you do is go directly to Access Pearson without clicking on course materials because you won't have a link. And it will ask you to pay for an access code, and you do that, and you will be in as well. And there should be no need to link up the course or anything because this is going through Canvas so that it will integrate with Canvas, meaning all of your grades will show up in Canvas. The assignments will show up when you go to Open My Lab and Mastering. And so they will be down here. There's not any assignments at the moment, but those will come pretty soon. I post homeworks when we finish a chapter. So when we finish chapter 1 will be the first homework. You'll see the e-text over on the left. Also, another thing worth mentioning is the study area. So this is where you go to take practice quizzes, practice exams. There's videos on each chapter. And so it's just a bunch of good study tools, study by chapter. And for each chapter, there's multiple choice practice exams and practice quizzes. Okay. Can everyone see her?
She's so cute.
Yes.
Absolutely adorable.
I looked around for her.
Adorable.
And I was like, where is she? Is she outside? But she was hiding under the table the whole time, right in front of me. So, yep, this is Gabby. So you'll see her on quizzes and on some multiple choice things. So she's kind of the unofficial mascot for the class. So she is always a good luck charm. So I think that's the main things I wanted to talk about as far as logistics for the course. Are there any questions at this point?
This might be a dumb question, but the homework that you sent out, like the chapter notes, not the
Yes.
homework, but the chapter notes, do we need to be printing those out?
So if you have like an iPad or a tablet, you can do it in that. If you don't, then yes, printing them is probably the best option. And I just like to do notes that way because it's kind of a nice balance between you scrambling to write everything on the board and you falling asleep while I just talk through a PowerPoint. So it's a way of bridging that gap and giving you some stuff to write, but not so much that it's overwhelming and you can't think about what you're doing. But the trade-off is printing it.
Okay, perfect.
Yeah. So I'm going to hop over to something else that no one has to worry about remembering or anything at all. It's just a way that I like to set the stage for what physics is and why at least I find it interesting and worth doing. So I'm going to have to turn my camera off because I use my laptop as a tablet as well as a two-in-one. And so it would look real weird seeing me on the camera. Like you'd be looking straight up my nose at this point if I still had the camera on. These are going to be me talking about the research I did as a graduate student because it gives a sense of kind of what physics is, what people are doing nowadays with physics. My graduate degree is technically in acoustics, not specifically physics, but it is an area of physics and engineering. I did research on things called sonic booms, and maybe you've heard of them. Has anyone ever heard a sonic boom?
Yes. I have heard of those too. Yes.
Okay. Have you heard them in real life or just on YouTube?
I don't think I've had the pleasure in real life.
It's not a pleasure, I promise.
I have heard them in real life. It's not a pleasure at all.
Okay, where did you hear them?
I can't even remember. It was
So I have a guess. Either an air show or something military related.
it was military related.
Okay. So that's the thing. You don't notice them in everyday life. There's not a lot of planes flying over producing sonic booms. And it seems like it would be useful actually because a sonic boom indicates that the plane's flying faster than the speed of sound. And that means it's flying fast, which is a good thing for a plane to do as far as getting from point A to B. But that unpleasant side of the sonic boom is it's very, very, very loud. So loud, in fact, that it has been illegal for a sonic boom to be produced anywhere over land except for those special cases of research facilities, military installations, occasionally air shows get provisions for them, but otherwise illegal since 1973 because they are so loud. And it's funny, like in the 1960s, it was just the wild west of sonic booms. They were doing it everywhere. And so many people called into the FAA and said, this is ridiculous. It's cracking the facade on my house. If they fly too low, it's breaking my windows. This has to stop. And so it was banned in 1973, anywhere over land. Over water is still okay, like if you're going across an ocean, but that's a pretty limited use case in the grand scheme of it. And so that's setting the stage for this. So what is a sonic boom? How does it happen? So you're going to see these numbers M. They just represent how fast something's moving compared to the speed of sound. M less than 1, M means Mach number. M less than 1 is something flying slower than the speed of sound, equals is at the speed of sound, and greater than 1 is faster than the speed of sound. In this first picture, you're going to see these bubbles. That's representing the sound moving away from the plane. Larger bubbles mean sound that moved away earlier. It was generated earlier in time. Closer bubbles were sound that was just generated. And so you can see that for something flying slower than the speed of sound, those sound waves are moving away before the plane catches up with them. And so they all kind of keep to their own separate areas, these different wave fronts of sound. But once you reach the speed of sound, the plane is keeping up with all of the sound waves it's generating, especially on this front piece. And so the sound waves do, in a real physical sense, start to bunch up, and it gets very loud there, very high pressures. Past the speed of sound, and that's why this is sometimes called the sound barrier, by the way, and breaking the sound barrier, because there is a lot of resistance to the motion of the plane at that point. It's called wave drag. It has to overcome it. But anyway, past the speed of sound, the waves still bunch up, but not along a line. It's along this cone, and that's called a Mach cone. So you have to picture kind of a 3D cone, not just this slice of it. So that is what we associate with a sonic boom. The waves move away perpendicular to that cone, and eventually someone down on the ground is going to hear that. It's going to reach them down here. That can be significantly louder than regular jet noise to the point that it sounds like a fairly nearby gunshot. And that is, in fact, because a gunshot is a sonic boom. That sound you hear is a sonic boom. What I researched as a student was how that can get even worse. As the jet flies faster and faster and faster, it's getting more and more ahead of earlier sound waves. That makes this Mach cone get narrower and narrower. So it starts out flying a little bit faster than the speed of sound, but then gets faster and faster and faster. It's accelerating. What that does is makes the sound waves that are moving away from the jet eventually converge on this surface right here that's called a caustic in red. And so those waves were already converged on the Mach cone, so already loud here. And then it's this convergence again of them on the caustic. What that means is, as far as how much louder we hear it, it's a little more complicated because the way we hear things is not what we'd call linear. It doesn't double when pressure doubles. we actually hear on kind of a logarithmic scale, but for things like sonic booms, it's even more complicated about how we hear it. But just think of the idea that if it's gunshot nearby for a regular sonic boom, for what we call a super boom, which is what you hear on the caustic, it's like a gunshot getting pretty close to your ear, like right by it. So, if sonic booms are illegal, super booms are very, very illegal. And they happen, unfortunately, whenever a plane accelerates past supersonic speed, whenever it turns, actually, and even in certain weather conditions. So it's more of a problem than you'd think. It's called acoustic, by the way, because this also happens with light. If anyone's drinking coffee right now out of a mug, then if you look down in your mug in the right light, you may see a little shape in it that looks something like, you'll see this kind of shape. That's actually a light caustic. It's a focusing of light in a special way. And caustic comes from the word burning in Greek. It's because, if you held up a magnifying glass of something in the right way, then you could burn something with it. And you might have done that if you were a particularly sociopathic child.
I was that particular sociopathic child.
Okay, well, you were just doing experiments, so you were born to be a scientist. But that focusing of light is very similar to what happens with sonic booms on this kind of caustic. And so there's a direct relationship between light caustics and sound caustics. There's also caustics when you look at the bottom of a pool, like those shimmering kind of lines you see at the bottom of a pool, those are caustics. Anyway, this was a problem. NASA's been researching this for a while, as have others. And so what they did to see exactly how loud a sonic boom on a caustic is, or a super boom, they set up this flight track. So how you look at this is a plane's flying this way up from the top, and that's generating the caustic, which is the dotted line. They put a bunch of microphones along the ground and just compared what the super boom pressure looked like at different points. Over on the left, you might notice that there's actually not a lot of those blue rays, which represent which way sound is moving. And what that means is that over here, you actually, in theory, don't hear anything. In reality, it sounds like distant thunder, miles and miles away. And then suddenly, if you start to get to the microphones right around this red box, it gets extremely loud, talking about that nearby gunshot, like right by your ear. And then if you move past that point, you start to hear regular sonic booms again. This is the area of interest, the red box, because that's where the caustic intercepts the ground. And that's where the sonic boom or super boom will be loudest. So people have spent some time figuring out exactly how sound behaves in that area, finding the pressure in that area. And they've come up with this equation that models that. And I'm going to show you the equation now, and it's not pretty, okay? So this is it right here. It is what's called partial differential equation, and you don't have to worry at all what that means, but the idea is it's modeling a bunch of different pieces of what's going on in that red box. So this is talking about wind. This is also wind in a different direction. This is some effects of the atmosphere called thermoviscous absorption and molecular relaxation. This is something called nonlinearity, which just happens with really loud sounds. And then this is something called diffraction and focusing of sound, which happens specifically in that red box. So, very complicated equation. No human can solve this equation. It's not one that I could sit down long enough and come up with a solution. And by solution, I mean what this P thing equals. That's the pressure. So what we do instead is have computers solve it. And it can take hours, days to solve equations like this. But what you get when you do that is a sense of the pressures going on in that red box. And so what NASA has done in the past decade or so is a bunch of flight tests where they did exactly this. They let a caustic be generated and picked it up on an array of microphones. and they compared what they recorded in real life to what this equation spits out. And here are some of those results. So the blue line is what the equation predicts. The red line is what was actually recorded during a certain flight test. Hopefully you see the equation does pretty good. The Z bar, if you're wondering, is just saying where you are in relationship to that caustic. So if I go back up here, Z bar being bigger than 1, being positive, means you're above the caustic. You're on the side where there is sound. Z bar equal to about 0 is where you're on the caustic, and Z bar negative is where you're below the caustic, where you should be hearing not very much. So that's kind of a reference here. So if you're significantly above the caustic, you have what's called an N wave, and that's what's generated normally by a sonic boom. That's what you associate with a regular sonic boom. And then something that gets reflected at the caustic called a U wave, but they're separate sounds. As you get closer and closer to the caustic, they kind of overlap each other. They merge into one. And eventually, right by the caustic, they're right on top of each other. And you get, if you notice, the pressure is almost double what it was in our first picture. So it's much louder on the caustic, just like we said. If you go below the caustic, negative, you get a much lower pressure and it's a much smoother kind of sound. And it actually sounds nicer. It's less intense. So what is the point of all this? Why bother? Well, NASA has been working on a technology that could potentially make sonic booms quieter so that they can be legal again, that they can be brought back. And so we can fly a lot faster. For us, that means potentially taking flights that take half the time someday. What they've been working on specifically is this thing called the X-59. X means experimental plane. PHYS means quiet supersonic technology. It's just a way of showing that there is a quieter sonic boom that could be made. And how they do that is through the shape of the plane. You may notice it's a very weird looking plane, and that's intentional. It actually causes not this N wave thing that we associate with like a gunshot, but a much more kind of spread out, jagged signature that looks like that. And for some reason, it does have to do partly with our perception of sound that sounds quieter to us, even if sometimes it produces higher pressures. That has been what they've been working on for a couple decades, and they have had some success with it, and it seems like it will work. Does anyone have any guesses of when this thing will take its first flight? Because you can probably tell this is a rendering of it. It's not a real picture.
2037.
2037. Good guess. Anyone else have any feel for it? It looks futuristic, right? It looks like this alien plane a little bit.
I would say 26.
Okay, so a little bit closer. It's actually even closer than that. It's this year. It's supposed to fly for the first time ever this year. And what they're hoping for when it flies is not a sonic boom that sounds like a nearby gunshot. It's what they call a sonic thump that sounds like a car door shutting 20 feet away. That's what they think it's going to sound like when you're on the ground. So if it works, then that is a huge leap forward and a good indication to the FAA that we can do this. We can bring back supersonic flight, but quieter. This is the first time I get to show this video because this is the first time this thing is real and fully built. It's just like a little sizzle reel. So it's just dramatic music. It's nerds trying to make stuff look cool, but it is kind of cool at the same time. I might not have shared sound. If not, you're just missing music. one last thing about this plane. Does anyone notice anything kind of weird about it other than its shape?
The additional wings up front.
So there is that, and that is also to help shape that sonic boom. So the geometry of the plane is very important. If you removed any part of it or changed any part of it, it would change significantly what we hear on the ground. So that is an important piece. How about I jump back to that last kind of frame we saw? Think about if you're a pilot.
The fact that the nose is like flat instead
Well,
of pointed.
There's that, but what is this thing missing?
Where's the cockpit's dome
Yeah,
that keeps you safe?
yeah. So it was down at that moment or not. They hadn't put it on actually at that point. So it does have a dome, but it doesn't have the front of the dome. There is no visibility out front of the plane, and it's because of that importance of the shape of the plane. If they added a front window, it would apparently change the sound so much that it would negatively impact how quiet this thing is. And so they had to remove a front window to maintain this shape. Instead, what they have is a camera system that simulates what they'd see out front. Like the camera points out and then they see a screen of what's going on out front. And they just got to really hope nothing fails with that. So I don't like that bit, but if it makes it quieter, I guess, we'll let the pilot handle that one. But that's an interesting feature of this plane. So why do I spend so long talking about my research other than to validate the years I spent doing it? Couple reasons. For one, if we look at something long enough, if we try and understand something, with enough time, we will get a very deep understanding of how it works and can look at even more complicated situations. Eventually, we can understand some things so well, at least to an approximation, that we can predict how they'll behave in situations we haven't encountered yet. And that's what this equation down here does. So physics lets us understand the way the world works a little better. But as you see with these pictures, even that nasty, nasty equation doesn't handle everything that's going on in real life. There's always these little wiggles, all these little differences between real life and what we think is going on. And so that shows that nature is always, in a lot of ways, a step ahead of us, and probably many, many steps. But when you stop and think about how complicated this equation is, how it can take us hours or days or weeks to solve on a computer, and yet it's happening instantly in real time, you really start to appreciate even more how much nature is doing in this. And, regardless of your beliefs, that's, I think, a very interesting thing that we wouldn't have realized unless we really studied this phenomenon and many others. The last thing that I find interesting is it lets you develop new technologies, that lets you look deeper into how these things work, lets you get further along in your understanding of the world. Now, engineering is kind of more the area where these technologies are developed, but physics lets you first understand the principles behind them. That's my three things. It shows you that you can understand things if you look at them hard enough. You can get pretty close. Second is that nature is still better at it than you and always will be. And that's incredible in its own way. Third is, with the knowledge you've gained, you can create new things for the benefit of mankind, for the benefit of your own understanding. And that's some things we'll hopefully get to touch on as we do this class. But of course, we have to start somewhere. We'll start at the ground level and just get those little glimpses at these interesting things about physics as we go. So that's my spiel on why physics is interesting. Now let's actually start talking about a little bit of physics. It is going to be kind of the routine that I'll post notes before we start a chapter. You'll hopefully have them downloaded. Sometimes I'll have a couple extra copies printed, but usually only a couple. And I guess we got 60 people in this class, which is still wild to me. But every time we start a new chapter, I'll have notes out before we start the chapter. Let's start talking about where physics sits in science and where science sits relative to everything else. So we're going to differentiate between science, art, and religion because more or less they have different goals. And so that's going to let us say that there's no conflict with them. That's the first thing we want to say in this class is no matter your beliefs, no matter your interest in other things aside from science, that doesn't conflict with your interest or love for science. Science is more or less about discovering and recording natural phenomena. You see something weird happen in real life, you say, I wonder how that works. And you start doing some experiments to get a better understanding of it. So you're trying to find order in everything that's going on around you. Try and finding underlying principles to organize how things work. Art is more about your personal interpretation and creative expression. So more about just finding beauty in things, and that's what lets you sleep at night. Religion is more the why. So science is studying like how things work, but doesn't ever necessarily get to a why things should work that way. So religion gets into that source, purpose, and meaning. Because each has a different aim in what it's doing, in most cases they don't really conflict. So we call art and religion non-science, not as something to talk down about those things, but to distinguish. Science and technology are in more of this symbiotic relationship. Each helps the other. So how does science help technology? How does technology help science?
Technology helps science by like being able to improve and like update things when needed and collect data for it.
Yeah, so how science uses technology is to do further experiments. Yeah.
Science helps technology improve and become more efficient, like better metals, better alloys, and things of
Yeah.
that such.
Yeah,
And technology makes science easier to do
yeah.
with better tools, better equipment.
I think that's a good way to put it. So technology applies science, develop new tools, products. And so this is kind of a back and forth process that's been going on since, I don't know, the Stone Age. The last one I want to distinguish is science and math. And a lot of people would argue on where math sits. Is it a science? Is it adjacent to science? What is it? Well, it is its own thing. And in fact, one of my degrees is in math. I really enjoy the abstract side of math where there is no physical restriction on what you're allowed to think about. Physics bounds you to the real world. At the end of the day, it has to explain what's going on outside. You can't just say, well, but I think it's really cool if you look at it this way. If it doesn't work that way, then you can't. In math, you can. So I like that side of it. But for science, how does math serve science, do you think?
Helps formulate theories.
Yeah. So it gives you, sometimes we don't see things directly, but if we do some algebra, do some rearranging of things, we start to see relationships we didn't see before. Is that what you're saying?
Yeah, because you said math is more abstract.
Pretty much that. It's that if you express things in terms of math, it's a little bit easier to check them, to extend on them, things like that. Verify, disprove, or expand on when expressed in mathematical terms. So, like we look back at that nasty equation, although it's gross, it's a lot better of a description than anything I could say verbally for what's going on. I can't sit and describe to a computer what it, well, with AI, you can get a little bit better at that now, but you can't sit there and just say, well, I think it does this, and this, and it spits out the correct prediction. But with math, you can do that. Okay, what else is math good for? I know a lot of you want to say nothing, and I promise we won't use a lot of math other than a couple little bits of algebra here and there in the class, so don't be panicked about that. But it is a useful tool. So how else does it help us? So actually, that one you said could go into this bullet as well. Provides compact expressions of relationships between concepts. So again, very vague definition or description, but it's just saying if we put things in terms of an equation, some algebraic relationship, then it becomes easier to see how things interrelate with each other, which is what you said about formulating hypotheses. Okay, there's one more, and this one's maybe not so obvious.
Take a guess.
Yeah. Go ahead.
I was going to say it like helps translate things over from like different people in different parts of the world because like it involves numbers, so it might be easier to stand in like actual formulations of like writing down and having to translate like that.
Like data analysis?
Yeah. If we describe things in normal everyday English or another language, there's all these ambiguities, all these things that we just take for granted about our understanding of the English language or other languages that are not assumed in math. Math is it's very clear cut what it's saying. As long as you're careful in reading it, it says exactly one thing. And so it's a little bit less ambiguous, a little less vague than everyday language. It's more precise. So it removes ambiguities of everyday language. For all those reasons, math acts as the language of science. It is how we communicate ideas in science. If you read certain physics papers, you will see that very few words are said, and there is a lot of math. Others, you'll see there's a lot of words and not so much math. So it's not the only way we have to express ourselves, but sometimes it is the better way. When we can speak in the language of science, we are able to reach a better understanding of what science is. Where does physics fall into this? Okay, I'm going to make some distinctions here to see where physics falls into things. And this is also not as clear cut as I'm making it look. So I'm going to distinguish between life science, living things, and then non-living things, the physical sciences. So can anyone give me some examples of life sciences?
Biology.
Yeah, perfect. The big life science. Okay. Can anyone give me more specific areas of life sciences? So like the study of animals specifically or plants specifically?
I was about to say zoology.
Yeah, study of animals. All right. What about plants? And that one's botany. All right, what about physical sciences?
Geology.
Yeah, study of rock formations.
Physics.
Yeah, physics is the big physical science. Perfect. Now, but I will say, like I said, not as clear cut of a distinction as it sounds. Physics actually does study living things. There's things known as biophysics, biomechanics. There's also on a cellular, why can I not say cellular level, that is studied by physics. So it's not as clear of a distinction. There's this other area of science that also has that thing of it studies both living and non-living things, but we usually think of non-living things when we talk about it.
Chemistry is a physical science.
Yeah. So that's the one where we think of mixing chemicals, non-living things, but there's organic chemistry. There's the study of compounds that make up life. And so none of these really fit exactly in their own column, but this is a rough distinction that can be made. Last thing I want to ask you is, what does physics study? How about you give me some examples of things physics studies?
Energy, interactions between like things like heat, light,
All these things are good.
electricity.
We'll fill in the rest of this list next time, but I'll just ask the question. What is energy?
Is it like the thing that like helps you like do work? Things like
Yeah.
that?
Okay, so what is work?
I assume it's just things that you do.
I guess what I'm trying to get at here is backing you into that corner of asking so many questions that you're not sure how to define things anymore. And that's where physics kind of does its thing, is tries to define those things, tries to understand them. And in that way, gets this more basic ground level foundational understanding of the way the world works. That's what it's trying to do, is all these things that underlie everything else. That's what physics looks at. So electricity is in so many things. We like to study that ground level thing of electricity. And so physics is the study of basic things, meaning things that are fundamental. So not simple, not that kind of basic, fundamental. So we'll list the others next time because I've already kept you a few minutes over and I apologize for that. I will not do that in class, I promise. Are there any final questions before we wrap up today?
How did we do attendance?
So I'm gonna be pretty lazy about it. Yeah. So what I mean by that is, so when we first start coming back in person, I'll have a sheet that you put your name on for the first like 2 weeks because they want us to be kind of strict about attendance for the first couple weeks to make sure people are attending, and so they can do like financial stuff on that. But after that, I just base it on the quizzes. So if you have unexcused quizzes, then those count against your attendance grade. I don't want to sit there and count up 60 people every day. Hope that you come to class because I try to bring some demos and things to keep things interesting and not just like what's in the notes. But I don't like to double count attendance against you either, because if you're missing class, homeworks may not be going so well, exams may not be going so well. So why count it against you yet another time with attendance specifically? So I'm not too strict on it in grade form. Okay, any other questions?
You mentioned seminars as extra credit. So how do you know if we attended a seminar? Are we like supposed to write something?
Yeah, thank you for asking that. So the first thing will be there will be a sign-up sheet at each seminar, and they send us those at the end of the semester. But I do like you to send me an email that just has a quick set of notes that you took from it. They do not have to be super detailed. They can just be like a big couple takeaways you had, because half the seminars are unintelligible to me because they're such specific research areas. So I'm not expecting you to know exactly what's going on sometimes, but just your takeaways in an email is all I want.
Do we have to attend every seminar to get the 5 total points?
No, so it's 1 point for each seminar you attend, and there are a good bit more than 5. It ends up being like 12. And you don't even have to, so if you can't attend seminars, if that time is it never works for you because of you have work or something, the alternative is those extra credit activities I mentioned. They're on Canvas, they can be done at home.
Are the seminars like study sessions, like where you're going to be going over?
No. So I don't put them on. What they are their talks that are done by other professors. I've done one before, but it's just them talking about their research or something they find interesting. So you'll hear ones about black holes and like modern physics research. If there aren't any other questions, then I will call it for today and hopefully see you all in person on Monday. I really don't like Zoom class because I can't do demos and then all the technical difficulties. So I really hope we're back in person on Monday. All right, you all stay warm and have a good day.